So today I'm here to talk about hacking a car, like not real car though, and how you can do the simulation to find like what actually we can exploit in terms of how dangerous it is. So it's going to be but interesting one. Now, just a quick introduction about me. I come from a web application security background. I'm a penetration tester and I have 4+ years of experience. I'm a recent graduate from the University of Warwick. I got 3 recent published CVs now. And yep, just a bit background about me. Now, imagine your car brakes stop responding. How fun it would be, right? You're on a way to conference today and you're driving a car, and when you're trying to hit your brake, it's not working. It is not just because of any mechanical fault, or it's neither an accident, but the security system protecting your car, it is drowning out of the signal. What actually happening here, what I'm trying to tell is, in the car, we'll be having a lot of operations going through. And when the network trying to interact with each other, and it won't be able to process the command that it needs to be done. So if the command, let's say you're gonna hit a brake and the command is not reaching the signal, and that's where the security is gonna fail over here. Why it is happening? We have the CAN bus. So the CAN is controller area network. This is something interesting in an internal part of a car. So you have a smartphone, right? So you have multiple applications. Let's say like you use Gmail and you use WhatsApp and you use a call. Every application has its own purpose. Now, in the car, we have the same, like we have multiple components. You have an engine, you have a brake, and you have a steering, and you have an infotainment. So all these has small components collectively called as ECU. They all need to talk to each other. So whenever you're trying to do some operations in the car, let's say you want to hit a brake and you want to accelerate and you want to use your infotainment, you're doing everything at the same time. The car has to process what the driver instructions are, like what is the instructions that you're giving, the signal, right? Now, this is car nervous system. So this is where it's gonna decide like what the user is trying to do. He's asking me to accelerate, or he's trying to hit a brake, or he's increasing his speed, etc. Right? Now, all these modern cars, we have like 50 to 100+ ECUs. Like these are like approximate numbers on one bus. Like we have multiple bus architecture involved in the CAN automotive system. Let's say you're gonna interact with each other. One example would be, you have a walkie-talkie and you don't know who's communicating with you unless until they are initiating a conversation. Hey, this is Alpha speaking, Gamma receive, right? But you will be able to figure it out that someone is trying to communicate and you will receive the information. Unless until they say who, you won't be able to identify what exactly the information that you are getting. The same concept here, whereas it involves internally inside the automotive, which is the CAN bus, and we have like multiple ECUs. You can call as engine, brakes, steering, and infotainment. The example which I said, like you can imagine your smartphone, like how it has many applications. Okay, what is the problem here? Now, these early protocols, which is these are developed in 1980s. These are mainly developed for speed and reliability, not meant for security. Why exactly we have this problem is there is no encryption or authentication in the base protocol. What you can do then? So that's where the simulation comes. You can start manipulating the messages. You can start manipulating the instructions that you're gonna give to your ECU. we saw what the ECU structure looked like, the CAN bus. Now, you're gonna hit brake, but the CAN bus is not reaching its signal. What's gonna happen? The system is going to face the problem, and that's where the failure is happening. Now, we have a concept, any node that can transmit, the ECU is gonna trust each other. The infotainment gonna trust brake mechanism. The brake mechanism gonna trust accelerator, right? So these are internally connected, and all these messages are trusted by default. So there are no verification mechanism between each other. But you can ask me like, okay, if there are no verification mechanism, then is it something serious issue? Yes, it is. But we do have a concept called secure onboard communication, which is recently being used by all the OEMs and automotive industry. What this will do is, this gonna add a message authentication code. With the help of this message authentication code, you can interact with the ECU, and this gonna verify what exactly the operation the CAN bus is receiving. Imagine you're hitting a brake command and it gets manipulated in terms of it's an accelerator and it's going to be a trouble, right? So it's going to verify what exactly the mechanism that you are trying to initiate, and it's going to add. You can take another example as digital signature. So it's going to add who's the sender, and the receiver should be able to verify, okay, this is the person trying to send this message, and in my end, I have to verify this, right? Now, most of these vehicles still rely on the legacy CAN architecture. So we have millions and millions of cars on road that is designed and in the market from 2015 to 2020, between that area, like 2010 to 2020, you can call, like millions and millions of cars. So those vehicles, these are mainly rely on the legacy CAN architecture, and the industry is not ready to adopt the SecOC. Why? So all those cars that is on the road now, it is highly impossible to give a updated SecOC communication to the existing vehicles. But few OEMs, they are into consideration about how they can integrate into their design and they can take it forward. So the key takeaway here is, in the CAN bus, the legacy architectures, the security was never part of the original design. So it's meant to be communicated for the speed and reliability. When you're driving a car, you might have noticed, you're gonna perform lots and lots of operation. You're gonna drive for like 100 miles, and in that 100 miles, you're gonna take a left turn, right turn, you're gonna accelerate, and you're gonna slow down, and you will hit brake. So all these are complicated operations for the architecture, automotive architecture, the CAN bus, to understand what the user is trying to initiate it. And it has to work in such a way that if you are trying to hit a brake, it should function within a microseconds, and it should work. If it's not, it's going to be in trouble. So what will happen if anything can be compromised? The milliseconds are very much important over here. And you have a legacy internet, like back in 2005s and 2010s, it will take like 5 minutes or 10 minutes for a song to get download. And we have the CAN bus. This is approximate speed. It is 8 times faster than the old DSL. But if you ask me, this would be enough? No, it is not. Why? Let me tell. Nowadays, we have a modern broadband internet connection. You can download GBs of data within like a minute, right? So we have that much speed capability now. CAN is designed to be made by speed, but for a car operating that too in milliseconds, it's very tight. Because I said like you'll be doing multiple operations together at the same time. Now what will happen? A new CAN message arrives every 125 microseconds. you can't keep accelerating your car, and you have to hit brake sometimes, and you have to operate your infotainment, and you have to use your left turn and right turn indicators. You'll be doing lots and lots of operations right when you're driving. So all those messages, it is happening within a seconds, and on top of it, there should not be any overhead, like such as you'll be adding a encryption detection mechanisms, and it has to process along. Now these, in a system with 125 microsecond window, 3 milliseconds doesn't just slow the things down, it can seriously stop safety critical commands from arriving at all. So when you hit a brake and the ECU is not getting that command, which means you're in a very serious risk. So what I did, this is where things get interesting. I've generated 5 attack types using Instrument Cluster Simulator. We have a dedicated open source project which is IC-Sim. You can take a note like IC-Sim, it is available on the GitHub, and you can simulate it as well. So I've generated 5 attack types for a virtual CAN bus to see how I can manipulate these attacks, manipulate the ECU, manipulate the CAN bus architecture. So what I did is, because there is no authentication, so that is why this is my MSc research project, and I wanted to make sure that I'm doing something that can be implemented in the industry as well. So, but no cars are harmed because it's a simulated environment, and it cannot be done without any funded project or research project as such. So there are 2 different categories over here. One is loud. So I've generated like 5 attacks, as I said, 5 attack types. One is denial of service. So you know what DOS is, like it gonna hit the bus with garbage frames. Like I'm gonna keep sending multiple requests within a matter of time, and it's gonna affect the CAN bus. And my idea is it's gonna detect loud. Okay, volume of requests are coming, it has to be blocked. So that's one of the loud mechanism. I mean, one of the loud attack type. And fuzzing, you send a random message by malforming some of the CAN frames. So that's gonna also classified under loud. And what can be quiet attacks, like you do something, someone is not noticing that. You're sneaking into a hall and no one is noticing that, right? So those type of attacks are quiet attacks. One is spoofing. You're gonna impersonate as another ECU. When you hit brake again, like you're gonna impersonate as it as accelerator. Come on, that's a serious operation to perform. But it will look real because that's why you're gonna do the spoofing. Like you might have seen all those phishing emails. It will look like a perfect real mail coming from a recruiter or real mail coming from an employee working in the company, but it's a spoof the content. And the replay attacks, you can capture and send a real message again. And stealth injection, you can capture the request, and for doing these type of attacks, you need to understand the CAN bus architecture and mechanisms and packet capture, the network, how it integrates and interacts with the CAN bus. So these stealth injection, it will look like a normal, but it is again a serious issue. I'll just quickly show a demo, not taking much time. Well, hope you can see now. Let's quickly launch it. So this is the open source simulation which I said. You have a live speedometer and also the controller. This looks like a joystick, PS4. Now, I'll try to control these by giving accelerating. If you can see, I'm just pressing the up arrow and the accelerator is rising. And you can left turn, this is right turn. We have these basic commands. Now I'll just get into the quick attack part. So, oops.
dump is one of the mechanism inside this. To vcan 0 is a network that I'm operating this IC simulation. Now this is going to capture all the frames that's going to have the communication over here. Now I'm trying to do the DOS attack, with which you can be able to see how these critical operations can be manipulated. Let's say this is, so what this is, CanGen is a random CAN generator for the network which I'm in, and I'm manipulating the speed and the direction. And if you closely observe, the car doors are also opening, closing, opening, closing. Right. So I'm sending multiple requests. So this particular command, which is -Z0, there are no frames involved. Till I stop, it's gonna keep capturing the request, and it's gonna keep generating a log. So this is a part of DOS mechanism. I mean DOS attack which I did. So we'll get out of the demo part quickly. And this is how all 5 attacks are generated with large volume of data set. When you try to classify your approach, you need a large volume of data set, right? All these attacks are simulated in an ICSIM environment with 5 different attack types. Again, every attack type has its own data set and volumes. Now, my mechanism, the approach which I followed is 3. One is rule-based, which got all the loud ones, which is we saw what are all the loud ones. DOS and replay detected. Stealth and spoofing, it got slipped through. So that is why, like, when there is a flaw, I want to make sure I'm working on any other approach as well. So that's why my alternative approach, which is machine learning only. The interesting part in machine learning is it flagged too much. It's better at quiet attacks, but 7% of false positives on the legitimate traffic. Out of 100 commands that you're going to give to ECU, 7 are real commands that it needs to get involved. So if those legitimate traffics gets filtered out, then again it's a crucial operation. So it needs to get flagged, right? Okay, what if we can do the hybrid approach? So that is where the solution comes. It's a best of both. The rules, it handles the obvious, the loud attacks, and the ML handles the subtle attacks, the quiet ones. So this is the only approach that I can think of now. So this is a number stats. When the rule-based shows 90% accuracy, FPR is a false positive rate, and we have 5% for rule-based, and the latency is 0.5 milliseconds. And you know the verdict already, so this is just a proof of that. You can ask, like, the ML and hybrid, it has both 98.7% as the accuracy. Now, how am I differentiating us with the help of false positive rate? False positive rate is where you need to be very concerned about rather than your accuracy. Because those 7% of your legitimate traffic, it should not get filtered out when the real user is performing operations. So that's the best overall balance. So here I have added the data set. As a note, everything is generated in a simulated environment. So the CAN frames which I generated for all those 5 attacks are 20.6 million labeled frames. I've classified everything under those 5 attacks, out of which I would say like 60% of the attacks are DOS, because that's where most dominant results are coming in. And I want to make sure I'm doing a mixed approach so I can get a better false positive rate, because my goal is to get a better false positive rate, not a good accuracy. So this is the key takeaway. A false positive is not just a noise. It can, silence a break command. In IT security, a false positive can be very boring. Like when you try to find a vulnerability and when you get to know it's a false positive, you'll be disappointed, right? Whereas over here, it is very crucial. It has to be addressed. It can literally silence a break command or vice versa. When you try to accelerate and instead of that, you're gonna hit a break command. Now, the bigger picture has a key takeaway for defenders and the industry people, and beyond course, we are dealing a lot of critical infrastructure in our day-to-day environment. Accuracy is a wrong metric in this case, not for any other simulation or in general. False positive rate matters more. Maybe whenever you're trying to do any other projects, you can go with lots and lots of algorithm out there. When you try to use machine learning, or we have lots and lots of algorithms, but you have to see what is your objective and outcome of your project is. And for the industry, as I said, the rules are for obvious threats, and I want to get a better hybrid model. And one thing to clarify is my model, it not gonna prevent any of the attacks. It's just gonna detect and it's gonna stop, and it's gonna give you a better rule or suggestions so that you can try implementing it on a real-time based systems. Other OT systems may also face similar trade-offs, but the implementation methodologies may be different, whereas the procedural can be same. Why this matters today? We have UNICE or 155 and some other laws that it from 2020-21, it has been mandate for all the OEMs to have a very strict laws in terms of connected vehicles. When you ship a connected car now in 2026, it's already vulnerable, as in like it can be manipulated. When you ship an autonomous car in 2026, all those driverless cars, it's very fascinating, right? Imagine there is no one, no driver to pick you up. You're just going to book a car and it's going to come and it's going to take you. That vulnerability, if it can be exploited, it can kill someone. Any accident can happen. So those are crucial commands. This research demonstrates how to prevent that, whereas maybe this is the time to implement. Thank you. The car survived finally. Everything did in a simulated environment. So you can find me on LinkedIn, Rakesh Elamaran, and that's my website as well. So this is one such project which I learned personally a lot of things when I was working in my dissertation. I come from a web application security background, but I wanted to make sure I'm experimenting something new when you're in a UK where the automotive hub and everything is. Yeah. Thank you so much. Open for questions.
So yeah, thank you for that. So the CAN bus is an integral to an ECU, which essentially runs a rate monotonic system, which assures that the way in which you build the software is safety critical by design. And there are many, many tens of years of work behind that, product development and deployment. So the car industry doesn't want to change any of that stuff, and they don't want to touch it. So my understanding of the approach that they're taking is an isolation model, and they're using virtual machines inside or at the point of the ECU to translate from the control signals from, the interrupt-based, non-safe, well, pseudo-safe radar and video systems to provide stimulus that goes into the ECU that may go through the CAN bus to the control systems. So in effect, with that privilege escalation, minimization, and complete isolation, why do we need to fix the lack of security in the CAN bus if it's no longer an accessible part of the car?
Okay, so that's an interesting question, because when you try to do privilege escalation or manipulate any other sort of operations, it can be crucial to the environment that you are in. Like, let's say you're trying to perform something, and irrespective of what you're trying to perform, if it gets something irrelevant and it's trying to execute something as that not meant to be executed. So that is why there is a secure onboard communication we have. So with help of that, you can add a message authentication confirmation with which you can able to verify it before you're gonna manipulate anything or kind of thing. That can't be implemented on the existing cars which is around the market now, right? Did I answer your question? Okay. Okay, got it.
Yeah.
Yep. I'm not getting that.
Yeah. Yeah, yeah. Yes. Yes. Yep. Okay. Okay. So you're basically asking, like, in cars, how effective the security can be? Okay. Yes. Got it. Okay. Yeah. Yeah, I got it. So it need not to be interconnected to the digital world, because, like, whenever you're trying to use your infotainment system, that's where you will be using your internet. And we have a concept called OTA, over the air update. Let's say you need to push something to your infotainment or push something to your ECU. You have to do with that mechanism, and that's where you will be using a real-time data transfer. Unless until if you just want to download application, you can just go to your infotainment and then you can just download it. But it can be manipulated as well with the help of some real-time operations. There are few case studies available as well, like how the infotainment can be hacked with the help of capturing the replay attacks and some other different types of attacks, with which you can control the entire automotive mechanism involved. Like, a good case study would be Tesla car hack that involved taking control over from the infotainment system. A researcher has breached to that, and Tesla awarded a crazy money for that to make sure they are fixing that flaw, and the researcher has to get what he deserved for this research.